So I'm going to sort of run through what we did at the end of class last time, because I think it's probably worth seeing for the second time, and sort of clearing things up. And also I made a mistake at one point, so I'll comment on the mistake. So again, we're doing singular value decomposition, and one fact that will be useful to us is the thing that we showed at the very beginning, that the null space of A is the same thing as the null space of ATA, right? And via the fundamental subspaces theorem, right, you say, well, if I take then the orthogonal complements of these guys, then I know by the fundamental subspaces theorem that the range of A transpose equals the range of ATA transpose. But the range of ATA transpose is just ATA again, right? Because A transpose A is symmetric. Okay, so that is the and let me just move this up here. Our range of A transpose is the same thing as the range of A transpose A. So erase this. Just remember, it's from the fundamental subspaces theorem. Okay, so first let's get the compact singular value decomposition. So what we did was we said, well, look, you have some m by n matrix, and you notice that ATA is symmetric, right? ATA is symmetric, and that gives you a couple of things. One, you know that all eigenvalues are real, right? Because it's a symmetric matrix, just like a Hermitian. You remember that for Hermitian matrices, all the eigenvalues are real. We also did a calculation, and we saw that all the eigenvalues are greater than or equal to 0. And most importantly, we know that there exists an orthogonal matrix V, right? So it is an n by n orthogonal matrix, such that the transpose ATA V is diagonal. Right. So there's a right, being a symmetric matrix by the spectral theorem gives you that there's an orthogonal matrix that diagonalizes you, right? So there's an orthogonal matrix that diagonalizes, gives a diagonalization of ATA, where these things are the these things are the non-zero eigenvalues of ATA. Right. So it has also some zero eigenvalues down here. Right. And let's let sigma 1 denote lambda 1 down to lambda r. Right. So it's the lambda 1 to lambda r are the non-zero eigenvalues of ATA. Okay. Right. So all we're using at this point is the spectral theorem. Okay. Okay, maybe I should. Sorry, I have different numbering here. So let me call this A, B, C, and this is step 1. So observation 1, we have a orthogonal diagonalization of ATA. Okay. Step 2. We say, well, let B1 denote the first R columns of B, let B2 denote the last n minus R columns. And remember that we introduced this notation, right? What sigma to the 1/2 means is that you just take the square roots of these things. E to the negative one, sigma to the negative 1/2 is going to be the negative square roots, and the square, the negative square roots. Okay. So right. So right. So you take V, right? V, and you split it into two pieces, right? So there's V1 and there's V2, where V is an n by n matrix, and this is R, and this is n minus R. Okay. Notice, of course, that the span of these V1's columns is the range of ATA. Right, and that V2's columns are the eigenvectors of ATA corresponding to the eigenvalue 0. Right? Does this make sense? This first statement, is that clear? The span of V1's columns is the range of ATA, right? Remember, right, what these columns are. They are an orthonormal basis of eigenvectors of ATA, right? Where these guys correspond to the non-zero eigenvalues, and these guys correspond to the zero eigenvalues, right? So these guys are a span of, these guys are an orthonormal basis for the whole space, right? And when you when you hit them with ATA, then you're going to get the right. You're going to get things in the range that are orthonormal to each other, right? So these things are right. So let me see it this way. The columns of V1 are an orthonormal basis for the range of ATA. Okay, which, by the way, is the same thing as the range of AT by our initial observation, by this thing here. Okay, so the columns of V1 are orthonormal basis for range of ATA. V2 columns are the eigenvectors of ATA corresponding to lambda equals 0. So what that tells you is that ATA V equals 0, right? For all of these I, for I being R plus 1 up to n. Right? So all these guys, when they get hit by ATA, they vanish. That is to say that all the VI are in the null space of ATA.
Just for I.
For I, yeah, again for I in I bigger than R. But remember what the null space of ATA was from our warm-up exercise. That's the null space of A. Right? From over here, we did this exercise, you know, at the very beginning of our discussion about the singular value decomposition. The null space of ATA is actually the same as the null space of A. Okay, and so, AVI equals 0 whenever I is bigger than R. Okay, so these guys form a basis, form an orthonormal basis for the null space of ATA, which is the null space of A. Okay, just
The VI formula.
the VI, so the VI these guys. Right. Right, because they are linearly independent, right? They're orthonormal, so they're linearly independent, right? And then there's enough of them. If you count how many there are, there's enough to span the whole space. So these guys form the everyone okay? Well, basically, what we're doing is we're just understanding what V is, right? What V is. So this V is an orthonormal. It's an orthonormal basis of eigenvectors of ATA, and we see that right, that these guys, the first R guys, are the basis for the range of ATA, and then the last guys are an orthonormal basis for this thing, for N ATA, which is the same as N of A, so null space of A. Okay. Any questions? We don't have to rush. There's plenty of time. Any questions? Yeah, Ellen.
Can you explain one more time why
Yeah.
the columns of VI form an orthonormal basis for the range?
Yeah. So think like this. What's the rank of ATA? What's the rank of ATA? R, right? It's R, right? And then each of these guys, you see that each of the VI here. So I'm going to take one of the VI. Okay, so let VI be one of these guys. When I hit it, I get some multiple of itself, right? So what does that tell me? That tells me that VI is in the range of ATA, right? So I have each of these columns is in the range of ATA, and I've got R of them, and they're linearly independent, and in fact they're perpendicular to each other, right? So I have enough of them to form a basis. They were already orthonormal, so they're an orthonormal basis. Same sort of argument goes to same thing goes here, right? You see that each of these guys is in the null space, and then you have enough of them. There are n minus r of them, and so they form an orthonormal basis for the null space. Okay. Any other questions? Everyone? So first off, we see that this thing is symmetric, And so we can find an orthogonal matrix that diagonalizes it. Okay. And the second thing we're doing is saying, well, what is this diagonal matrix? I mean, sorry, what is this orthogonal matrix that we're using? And we make some observations about it. We say, okay, well, the first R columns are an orthonormal basis for this. The last n minus R columns are an orthonormal basis for the null space. Okay. I'm going to walk outside for a minute. So just think, if you have a question, think about it.
What's going on now?
Did we ever learn why the rank of ATA is R?
Yeah.
What's a range
We
again?
did that last class.
Is that
Yeah.
okay?
It was like one of the
Somewhere.
Orthogonal basis, range, like
I figured it was just
There's like
I read you a few thoughts somewhere, it would make sense.
Oh, that's right.
Yeah, like now, right now we're just accepting.
Yeah, the basis that. Remember, he was like, this is the
Yeah, so
stupid
we showed
definition.
the ranks are the same.
But what does that mean?
Why is the
Like,
rank
if,
the number of non-zero eigen? No,
I don't
yeah,
actually know.
but why is the rank equal to the number of non-zero?
I feel like, you know the radio show Car Talk?
Yes.
Ha! I'm back, and you actually do have questions. So what I think, anything confusing? Anything confusing? Yeah, Mia.
Why is the rank of A equal to R?
Why is the rank of A equal to
Is that the
why is the rank
question?
of ATA equal to R? Right? Well, that will also give you that the rank of A is equal to R
Mhm.
because the rank of AT is equal to the rank of AT. So
Is it because the pivots of A correspond to how many non-zero eigenvalues there are?
think like this. Let's see. So think like this. This thing here is an orthonormal basis, right? This thing is right. V is this thing here. V1, V2, VR, VR plus 1 to Vn. Okay, where in fact the V1 through Vn is an orthonormal basis of Rn, right? But it's more than that. It's an orthonormal basis of eigenvectors.
So is it by the rank? Like if you have the null space of A,
Yeah.
the nullity
Yeah.
plus the rank equals.
Yeah, you could think of it that way. That's certainly a valid way.
Okay.
You say, well, look, what's the dimension of the null space? N minus R. What's the dimension of the rank? R. So rank of ATA is R. Other questions? Yeah, that's maybe a bumbling one at the beginning. Okay, yeah, so the rank of A is rank of A and is equal to the rank of ATA, and they both have rank R. Okay, other questions? Okay. Will we get past the compact singular value decomposition? I don't know.
Can we go over very briefly an orthonormal basis?
Yeah.
It's like it's analogous to the ease, the standard
Yeah,
basis.
yeah. So orthonormal basis just means that the vectors are all perpendicular to each other,
Okay.
and they're all of length 1.
Okay.
Okay, they're all perpendicular to each other, and they're all length 1. So if you take, for example, if this thing has as its columns all orthonormal bases, all orthonormal vectors. Okay, suppose that its columns form an orthonormal basis, right? Then if I take V transpose and hit it with V, then what's going to happen? I'll get the V's like this, right? I'll get V's like this. And you see what happens when I take the dot products. These guys will give me V1 against V1. That's the norm squared. Well, the norm is 1, right? When I take V1 against V2, I get 0 because they're orthogonal. V1 against V3, I get 0, and orthogonal. V1 against Vn, they're orthogonal. V2 against V1 is 0 because they're orthogonal. V2 against V2 will give me the norm of V2 squared, but that's 1 squared, so I get 1 here.
So you get the identity.
You get the identity matrix. So for a matrix that has a matrix that's orthogonal, namely a matrix whose columns form an orthogonal basis, its inverse, its transpose is its inverse. Okay, so orthogonal means that its transpose is its inverse. Okay. Okay. Other questions? Okay, so that's V. Now we understand V, I hope. Okay, and we made some observations that the main one being that V1 transpose plus V2 transpose is the identity matrix. Okay. So this is what it. If we look at AV1 sigma 1 to the negative a half, sigma 1 to the half V1t, we see that that's equal to A V1. These guys cancel each other out. V1 transpose. That's equal to A V1 transpose plus V2 transpose. Because of the previous fact, right? A kills V2, right? The null space of AT, remember, these guys span the null space of A transpose A, but the null space of A transpose A is the same as the null space of A. So A will kill V2, just as A transpose A kills V2. Okay, so this is, I'm adding on a 0 here, and this is what I got wrong last time. Okay, I mean, it's right, but I didn't explain it correctly. Okay, and so we get A itself. Okay, right, so if we let E1 be AV1 sigma 1 negative a half, right, which is in an n by n matrix, we have just seen that U1 sigma 1 to the 1 half V1t is A. Right. Which is called the compact SVD. Yeah,
Why do we have to add on the V2 transpose if we know that V1 is an orthogonal basis and V1 transpose V5?
Yeah, maybe we don't need to. Let me think about that. V1 Yeah, I think you're right, actually. Yeah, you're right. I think we don't need to. V1 is like that. V2 transpose. Let me think about that. I'm going to leave it as it is, but let me think about that. At least I know it's okay. It's okay this way. But you might be right. Let me think. Okay. Yeah. In fact, I was just thinking about that this morning. Like, it should be that you don't need to add on that, but I'm not sure. Okay, so we have this thing, the compact SVD. Okay, and notice that U1, this thing equals AV1. I was going to do student evaluations today, but if we stop here, it's just going to be too ridiculous. Because the next class, we'll probably have to start over. It's like some sort of hell. Okay. Okay. All right. Okay. So here we go. Now that's the compact SVD. Let's go onwards. Now, let V be V1, V2, of course, as we had before. Let's consider. I probably don't need to include this, so it interrupts the line. So consider U1. Okay. Right. U1 is AV1 sigma 1 to the negative 1/2. Right. Which is the same thing as AV1, AV2, AVR. Sigma to the negative 1/2, sigma 1 to the negative 1/2 down to sigma r to the negative 1/2. Okay. This thing is an n by r, this thing is an r by r. Okay, right. And then if you multiply it out, you see that you get AV1 over sigma 1 to the 1/2, AV2 over sigma 2 to the 1/2, AVR over sigma r to the 1/2. Okay, which we'll denote by U1 through UR. Yeah, Mia.
Why is that equal to U1, not
U1, right?
I just don't get why we're all, like U1 equals AV1, but then we go all the way to R in the matrix.
What do you mean all the way to? What do you mean all the way to R?
Like, why is A times V1 equal to A times V1, A V2, A VR?
Oh, well, this is the matrix, and these are the columns.
Oh, the
So,
big
yeah.
matrix. Okay.
This is the matrix V1. Sorry.
Okay.
From up here, and each where V1 is, the first R columns of V.
Yeah.
The first R columns of V, right? And then you hit it on the left with A. The left multiplication acts column-wise, right? So you just hit each of these guys. Okay. Okay, so that's U1, right? That's U1, and there's an easy claim that the U1, the UR, are an orthonormal set here's how you check it. You say, okay, well, let's take ui against uj. Okay. Ui against uj, which is this thing, right? You know that you can move the matrix to the other side if you transpose it, right? Remember that A B W is the same thing as V A transpose W. Right? You can move the matrix to the other side as long as you transpose it. So it's the same thing as ATA VI over V lambda I A VJ, oops, VJ over lambda J. Right? But remember what the V's are. They were eigenvectors of ATA. Right? The columns of V were the eigenvectors of AVA, and so we're going to get ATA, excuse me, and so we get just lambda I VI over lambda I, which is VI. Oh, sorry, these should be square rooted, right? Right? And you see what happens, right? If I is not equal to j, we get 0, right? So what do we get? We get lambda I to the 1/2 over lambda j to the 1/2 VI VJ. Right? What do you see happens? If I equals j, what do you get? One, right? Because you get VI against VI, it's orthonormal, so the norm squared is 1. And we would get lambda I to the 1/2 over lambda I to the 1/2, that'd be 1. Right? So you get 1 if I equals j, and you get 0 if I is not equal to j, because these things are orthonormal. Again, these are orthonormal, so if you're taking different ones, they're perpendicular. You get 0. Okay.
It'd be so hard to be dyslexic and have to look at the I's and J's.
Should I
It's kind of
make them longer?
Is anyone here dyslexic? I'm gonna feel
How
your shit.
lucky.
Hey, you can't ask that.
Oh. Can't
Okay.
ask that?
Yeah. Or I mean, you can, but it's rude, right?
Oh. Sorry.
Yeah, there was a professor at University of Chicago who I think was dyslexic, and it was hard to follow him in class. There was sort of a joke about his notation. He would often write down wrong letters. He'd say, "So suppose you have a manifold M," and then he would he would go on. The joke was that he used only 2 symbols in class, and one was an alpha and the other was a gamma. But the alpha was rotated counterclockwise 45 degrees, and the gamma was rotated clockwise 45 degrees. So anyway, it was hard to learn from him, or rather, one had to really focus to learn from him. But he was a good mathematician. Okay, here we go. So, right. So these guys are orthonormal. Okay. There's R of them, right? So notice, right? The UI, U1, the UR are orthonormal, and there are R of them, and they all lie in the range of A, right? Because they're all A of something, right? They're all AVI. They're all A of something, right? So right, which has dimension R, as we noted earlier, right? And so these guys are an orthonormal basis for the range of A. Okay, so what we're going to do is we're going to fill up, we're going to fill this up to an orthonormal basis for the whole space. Okay, so extend U1, UR to an orthonormal basis for the whole space. Right? So that is you i.e. choose an orthonormal basis for RA curve, right? We already have an orthonormal basis for the range of A. We need to have an orthonormal basis for the orthogonal complement in order to fill it up, right? So choose an orthonormal basis UR plus 1 to URM for the range of A curve. Okay. And then let U be that full matrix. U1 through UR plus 1 through RM. Okay, so, right, and now maybe, and also recall that we let V was V1, V2. Okay. Okay, so you see, you know, you have from the compact SVD, you have this guy U, but you extend it. You know, it's just part of an orthogonal matrix. It's not square, right? So you basically throw in more basis vectors to make it a square. So now we've got U, which is an orthogonal matrix, and we've got V, which is an orthogonal matrix. Okay. And now we have the full SVD. You say then U sigma VT is U1, U2, right? That's called this part U1, and this part U2. U1, U2. Sigma, you recall, was this guy. Right. This is an M by N matrix. Right. This is an M by M. This is M by N. And then V1 transpose, V2 transpose. Okay. And then using your knowledge of how matrix multiplication works, you know, this is going to be it's going to look like this: U1, U2. We'll multiply the last two. You get sigma 1 V1t, right? And you get 0 down here. Right. And then let's multiply these guys now. and you get U1 sigma 1 V1 T plus 0. But we saw what sigma 1 U1 sigma 1 V1 T was. That's it. Yeah, Mia.
Is this the full SVD?
Yeah, so
Okay.
so this is the full SVD. You see that we realized A as a product of this diagonal rectangular guy here, and so we realized it as a product of an orthogonal matrix, this diagonal rectangular guy, and then orthogonal matrix. Yeah.
And sigma 1 is the
Sigma 1 was lambda 1 to lambda.
okay, and then R,
R.
and then all the other ones are. It doesn't matter if you fill in the lambda R plus 1 because
Those
their
are all zero.
eigenvectors are zeros.
Yeah, those are.
Or their
those-
eigenvectors times A equals 0.
Those were all 0. I mean, the eigenvalues past this point are 0.
Okay.
Yeah. There are eigenvalues, but they're 0. Yeah. So this sigma 1 is the positive eigenvalues of ATA.
And there can't be negative eigenvalues? Did we
Right,
prove that?
because we showed at the beginning that the lambda could be realized as this sort of thing where V was in the lambda, and so this was always positive,
Okay.
not negative. Okay, so this is the singular value decomposition. This is the singular value decomposition. Okay. And let me just put up a few observations. Sorry to hold you over. Let me just put up a few observations that we've basically already made. I'm just going to collect them. Just to remind us. One, the VI are orthonormal eigenvectors of ATA, where V1 through VR are an orthonormal basis of ATA's range, which is the same as the range of A transpose. The last n minus r of them are an orthonormal basis of the null space of ATA, which we saw was the same thing as the null space of A, which by the fundamental subspaces theorem is the orthogonal complement of the range of A transpose. 2, similarly, the UI are orthonormal eigenvectors of AA transpose. Maybe that's not clear. I'll try to explain it next time. But again, with the first R, an orthonormal basis of the range of A, which is the same thing as the range of AA transpose. And the last M minus R, an orthonormal basis of RA perp, which is the same as N a null space of A transpose, which is the null space of A transpose. Just some names. The VI are called the the right singular vectors of A, and the UI are called the left singular vectors of A. Again, I just want to make one quick observation. Notice that AV equals U sigma, so AVJ equals lambda j to the half uj, where j equals 1 to n. This thing is usually denoted sigma j. The lambdas to the half are usually denoted by sigmas and called the singular values. Okay, and similarly, ATU is V sigma transpose, so A transpose Uj brings you back to the VJs, where J equals 1 to M. Okay, so there's there are relations between left and right. Relations between left and right singular vectors. Right? That the UIs you get by hitting the VIs with the A, the Vs you get by hitting the Us with A transpose. Okay. So that's the singular value decomposition. Okay, and next time we'll see what's good about it.